Good morning, students. Today I will be delivering a lecture on three-phase star and delta system numericals. So, in the first numerical, there is a balanced three-phase star connected load of 18 kilowatt, taking a leading current of 60 amperes when connected across a three-phase 440 volts 50 hertz supply, and we are required to calculate the nature of the load and its reactance value. All, we should understand that the connected load is given as 18 kilowatt, so we should convert it into the SI system as 18,000 watts, and the three-phase supply system is for 40 volts. So it is to be kept in mind that the line voltage is 440 volts, supply voltage is the line voltage, and it is also given that the leading current of 60 amperes is this. So whenever the current is leading, it means that it is having the capacitive component, because whenever there is a capacitive component, the current is leading the voltage. And we have to calculate the phase voltage, and phase voltage in the star connected system is given as Vp is equal to VL upon root 3, which is calculated as 254 volts. Line current and phase currents values are same in the star connection. So line current is given as 60 amperes, so the phase current is also 60 amperes. So why we are so interested in calculating the phase quantities? Just because the load impedance or the load is always connected to the phase. So on substituting the phase values of voltage and current, we get the impedance as 4.234 ohms. Next part is to calculate the power factor. So it can be calculated using the power formula, and the load is given in kilowatt or watt, which indicates that the power is real power is given. So we have to apply the formula of the real power. P is equal to 3 VI cos phi, where V and I are the phasor quantities given in RMS terms. So Vp and Ip phasor quantities are substituted to get the cost, and since it is given in the numerical that the current is leading, so the power factor is also leading. And since the power factor is between 0 and 1, so it leads to the conclusion that the load is not pure capacitive load, but it is the RC load. In the pure resistive circuit, or when the load is pure resistance, the current and voltages are in phase, so zero angle of phase difference is there, so cos phi is 1. But in the pure capacitive circuit, the current is leading by 90 degrees, so the power factor becomes 0. So here, since the power factor is between 0 and 1, so it results us to the conclusion that the load is RC. So once the load is clear, the nature of the load is clear, then we can calculate the its component, resistive component and the capacitive components, or the reactance and the resistance of the load. So from the power triangle as shown in the figure here, Z is in the hypotenuse and X and R the perpendicular and the base. So Z cos phi is equal to R and Z sin phi is equal to X. So in this way we can calculate the resistive and reactive components of the load. So R is equal to Z cos phi, Z is known to us, cos phi is known to us, we can calculate the value of the resistance. we can calculate the value of sine phi, and on substitute of sine phi in the z sine phi, we will get the resistance of the load. So the primary part of our numerical here, but if at all we want to calculate the capacitance, the magnitude of the capacitance, we can calculate using the formula 1 omega c. So let's move on to the next numerical. So in this numerical, a three-phase, three-wire star connected system is there, and 150 volts is given between two phases. So in some of the numericals, the line voltage is not clearly defined. It is given as the voltage between two phases. So it should not be confused with. So it should be clear that it is the line voltage, and each phase has the impedance of Z equal to 5 angle minus 30 degree, and we are required to calculate the current in each phase and total power. Okay, so again, line voltage is given to us, and line voltage is given as 150 volt, and the phase voltage can be rated using the formula Vp is equal to VL upon root 3, and magnitude of the impedance is known to us, so it is substituted to get the value of current as 17.32 amperes, and power factor is the cos phi, and it is written as cos 30. So how we can judge that it is cos 30 and not minus cos minus 30? Although mathematically, if we say that the cos 30, cos of minus theta is cos theta, so mathematically it does not affect us. So cos 30 is equal to 0.866. But here it is given as power factor as a leading. So how come we conclude that it is a leading power? The angle of the impedance is given as 5 angle minus 30. So if we want to calculate the current using the vector algebra, so if we substitute the z as 5 angle minus 30, so z is in the denominator, so current ip will be 17.32 angle positive 30. So it means that the current is leading the voltage, hence we will get the leading power factor. Now the last part is to calculate the total power. Again, in the numerical, we should be smart enough that if the real power, reactive power, apparent power is not defined or asked clearly, let's go for the real power. Value of phase voltage, phase current, and the power factor, we can get the result in SI system as 3897 watts. Later, it can be converted into kilowatt as per our convenience. Again, a thing which is to be kept in mind is its terminologies. In the sign convention, K is represented as small letter and W is represented as capital letter. So this is to be kept in mind. If at all this numerical demanded to calculate the apparent power as well, so that would be 3 Vp Ip. Similarly, if the reactive power is also required to be calculated, then using the formula 3 Vp Ip sin phi, we can calculate that. So in this numerical, when the balanced impedances are connected to delta across three phases, So now we are dealing with the delta connected system. 500 volts 50 hertz supply is given, and the line current drawn is 20 amperes at 0.3 power factor lagging power factor is given, and we have to calculate the resistance and inductance per phase. So here the line voltage, supply voltage is line voltage, which is given as 500 volts, and in the delta connection the line voltage and phase voltages are same. So next part is to calculate the phase current. Ip is equal to IL by root 3, and the line current is given as 20 amperes. So dividing by root 3 we get the phase current as 11.547. Power factor is given as 0.3 lagging, it's already given, and again since it is between 0 and 1, so it is the RL load. Okay, impedance per phase Zp is equal to Vp upon Ip. Voltage is known to us, Ip we have just calculated, so on dividing we will get the impedance per phase as 43.3 ohms. Now using the power triangle, the Rp is equal to Zp cos phi. So Zp is 43.3, and when it is multiplied by 0.3 we get the resistance per phase as 12.99 ohms. So next part is to calculate the inductive reactance per phase. Xp is equal to Zp sin phi, and substituting the value of sin phi from the formula cos square phi plus sin square phi is equal to 1, we get the inductive reactance as 41.3 ohms. Now we are required to calculate the inductance per phase. So x is equal to 2 pi fl as explained in the previous numerical as well. So substituting the values of xp and frequency, which is given as 50, we can calculate the inductance as 0.1315 Henry. It can be converted into millihenry as 131.5 millihenry if required. Okay, now we will move to the another numerical based on the delta supply system. So here the three impedances of 20 plus 15J ohms are connected in the delta across 400 volts. So the impedance is given as in a vector form or R plus XJ form. Okay, in the lower classes 11th 12th we have learned the complex number as x plus iy, but in the electrical engineering we use R plus XJ as the J operator or the I operator, which was given there, which which means that I square is equal to minus 1. So it is here replaced by J, and we are required to calculate the line current, power factor, and the total power consumed. So line voltage is given as 400 volts, which is equal to the phase voltage. Since it is a delta connection, resistance per phase is given as 20 ohms, and inductive reactance per phase is given as 15 ohms. So from the impedance triangle, in the impedance triangle, Z is the hypotenuse and perpendicular is reactance and resistance is in the base. So using the Pythagoras theorem, we can calculate the value of impedance per phase Zp as under root of Rp square plus Xp square, which comes out to be 25 ohms. Now to calculate the current in each phase, Vp upon Ip is equal to Zp. So using this formula, voltage is known to us, impedance is known to us. We can calculate the phase current by dividing these quantities as 16 amperes. Now the line current IL is equal to root 3 Ip. So Ip is 16. So we get the line current as 27.7 amperes. Next is the power factor. Power factor is again calculated using the impedance triangle. Cos phi is equal to base upon hypotenuse. Base is our resistance and hypotenuse is our impedance. So 20 upon 25, we get 0.8 lagging. So how this lagging situation has occurred, although it is not given in the numerical. So the idea is very simple, that if the reactance is given as capacitive reactance, then it is fine. Otherwise, by default, it is taken as inductive load or the RL load. So we can say that the cos phi or the power factor is lagging. Now to calculate the total power, P is equal to 3 Vp Ip cos phi, same formula which applied in the previous numerical. So 3 into 400 into 16 into 0.8, we get as 15360 watts in the SS system, which can be converted into 15.36 kilowatt. Thank you.